Hello, I'm Markus, and I'm with the German National Library of Science and Technology, as well as with Pangea, the data publisher for Earth and Environmental Science at the Marum Center for Marine Environmental Sciences in Bremen, in Germany. Today I'm going to present an ENVI Plus science demonstrator that shows how new particle formation events can be analyzed on interoperable research infrastructure and e-infrastructure. This work was done in collaboration with some of my ENVI Plus colleagues, in particular Marcus Fiebig, Leonardo Candela, Giuseppe La Rocca, Enol Fernandez, and Alex Hardisti, and also received substantial and important input from the relevant research community in aerosol science. So what are new particle formation events? So these are events whereby new particle formation, particular matter is formed in the atmosphere. And over a couple of hours, usually during the afternoon, early afternoon, during the day, the diameter size of this particular matter increases in size over time. And aerosol scientists use this primary data to detect these events by analyzing the data, the primary observational data. And then they describe these events for their properties, in particular, for instance, the classification, whether there is a very strong event or a weak event, as well as the duration when the event begins and when the event ends. And these events are studied for climate change because they're relevant to climate change, aerosol, so they want to quantify the aerosol formed, as well as for respiratory health, because of course particles have a negative effect on human respiratory health. This figure shows you how researchers use visualization methods to detect new particle formation events as they occur during a particular day at a particular location. And you see here on the x-axis a day, 24 hours, and on the y-axis you have particle diameter size ranging from about 3 nanometers, which is the detection size of the particle for the current systems, the sensors, up to about 100 nanometers. And you can see here around noon, we have a high concentration of particles in yellow here, which are originally at the beginning very small here around 10 a.m. And then they grow in diameter size over a couple of hours in the afternoon. So from about 3 to about 25 nanometers. And this is a visualization of primary data of sensor or processed sensor data that the researcher generates to determine whether at a particular day and location a new particle formation event. So these are the signals, this what they call banana shape here. This is the signal in the primary data that researchers look after to determine whether an event occurred. And given the detection of events, then they describe these events when they occur, so what starting point and when they end, and also they calculate a number of other attributes, in particular also the growth rate of the particular matter, and also they classify according to one or potentially multiple schemes the events. In this case, it's a clearly visible event, so it will be a so-called class 1A event. So there are a number of researchers. In fact, the global estimate for the number of this community, size of this community is about several hundred researchers that do this kind of research in aerosol science, study new particle formation events. And they have, traditionally they do this individually. So they develop their own source codes. They use different platforms for this, different languages, programming languages, for instance, R or MATLAB, to do this kind of research. In particular, the processing of the primary observational data, the visualization of the data, as we saw in the previous slide, as well as the acquisition of the derivative data, data about the new particle formation events. So when, where they occur, the classification, the duration, the growth rate. And the way they encode this information about new particle formation events is very different. Depends on the researcher sometimes, or the research group. Some people use Excel to curate this data. Others have MATLAB matrices in comma-separated value files. And generally, the data is stored also in on the hard drives of the researcher. Some groups are perhaps reacquiring this data systematically to archive it, and others don't. So the practices are very dependent on the community, or even sometimes on the individual researcher. But generally, here schematically, the researchers take data from research infrastructures. That's the primary data that they visualize, and then they use computational environments like R or MATLAB or Python to analyze this observational data, to visualize it, and compute, extract properties from the primary data about these events, and then they curate the derivative data about new particle formation events in various ways, sometimes in Excel, sometimes in comma-separated value files or XML files, and so on. And this data, as I said, is generally curated and stored, and at least at the beginning, on the disks, on the hard drives of the individual, of the workstations of the individual researchers. So there are a number of challenges with this approach. So on one side, we have high syntactic and semantic heterogeneity of the derivative data, because the researchers do it as they best, as they think is best, or in their own way, or the research group has a particular way of conducting this kind of analysis. So you have a consequent high heterogeneity among the groups of the resulting derivative data about the new particle formation events, and therefore also a difficulty of integrating across the groups in the community the derivative data about new particle formation events, and potentially do more global studies about this phenomena. Another issue is that the semantics of derivative data are often implicit. So how the way the information about the new particle formation events are stored as comma-separated value files, as MATLAB matrices. The meaning of that data is implicit. So you need to be an expert in the field to understand what this data is about. Of course, sometimes there is metadata, but the metadata is also typically human readable, and for machines very difficult to access and read and interpret. The third point is that there's a lack of systematic acquisition, of direct acquisition of the derivative data about new particle formation events. So the data that is generated out of analysis in infrastructure. So generally this is again stored via MATLAB on the disks of the workstations of individual researchers. And then it's a question whether this data is then subsequently acquired by a research infrastructure and also curated and preserved over a longer term. So these are three challenges which we are trying to address with a proposal for this community, whereby the various research group and individual researchers would use a virtual research environment that here is provided by the D4Science infrastructure. And this virtual research environment includes the necessary codes for the classification of these events, so the detection and classification of events, and also the processing of event information, for instance, to compute mean durations of events and so on. And I will demo this later. And these codes are here implemented in Python and run in a Jupyter environment that is hosted at GGI. And the data generated about new particle formation events, or for instance, the mean duration of events, things computed out of analysis, are now not stored on the disks of the individual researcher, but directly in the virtual research environment and cataloged in a CCAN catalog, which is also provided by the D4Science infrastructure. And on top, the data generated is semantics. So we use here semantic web technologies, in particular RDF and some ontologies, to make sure that the meaning of the data generated out of analysis is also captured and curated together with the data. Okay, that's the proposal, and I'm now walking you through the how this works with the D4Science and the virtual research environment. So this is the login here. I have a user account, so the researcher needs to create a user account and then sign in. And after signing in, you will see here there are a number of virtual research environments, and the one relevant here is called particle formation. I can select this virtual research environment, and you can see here a number of options in the menu. Most important here is the Jupyter environment as well as the catalog, and I'm opening the catalog in another tab here just to show you there is some data here cataloged already, and perhaps we can quickly take a look. So there are a number of PNG files, so the plots, as well as the descriptions as turtle files and some mean durations. And I'm coming back to this after showing you now the Jupyter environment. So this is Jupyter. It's a standard software that you can use to run and implement code in various languages. And I have here 3 notebooks, one for classification, so the detection and classification of new particle formation events. There is a little bit of code here. You need a G-cube token to run this, and then there is a little bit of code here for that implements some specific functions to plot and visualize and record information about new particle formation events. Below, we see here the classification, so the user can select any day here and a specific place of analysis. Here we use Hytila. Hytila is a place in Finland. And the next step, so after configuring the day and place, the next step is to plot, so fetch the primary data about the aerosol concentration over time from a research infrastructure. And here we use a SMER, so the Finnish station for measuring ecosystem atmosphere relations, to fetch this data live and then plot and visualize it here. And this is a result as I showed in the slides. So you can see here strong event on April 4th, 2013 in Hytila. And the researcher can now interpret what she sees here. Okay, we have a strong event, so this is classification according to some scheme. This will be, for instance, classification 1A, and we can also acquire or describe this event for when it starts and when it ends. So this is typically looked at a lower nanometer size, 3 nanometers. So when the event starts here around 10 o'clock and when it ends roughly 12. And the researcher can now record this kind of information about events. And by doing this, we have a new entry in the catalog directly. So this data is directly cataloged, and I can show you this here. You can see for the 2013 April 4th, we have here a description about the event. We have some metadata here about this entry in the catalog, and as well as here the description of the event. And this is an REF description following some schema. And I'm not going through this, but it's a machine readable description of the event that has information about the classification, where the place where it occurs, the time when it occurs, and as well as some provenance information when the activity was executed, when it was started, and yeah, we have here information about the entities and so on. I'm coming back to provenance in the last notebook. So this is the machine readable description of the event. So we don't have just the labels for the day, location, and the starting time, the ending time, the classification, but we have here a semantic description of the event that is also meaningful to machines. So I'm going back to the catalog. Going quickly back to the catalog here, to the first page. I have done this for several event descriptions, not just April 4, 2013, but also on other days, as you can see here. But I'm going back now to the processing of new particle formation events. So we have here in the catalog descriptions for various new particle formation events that occurred in Hytila at various time points. Now we can process this event information, for instance, to compute a mean duration, an average duration of events at Hytila. And for this, there is another notebook. Again, G-cube token. You have a few methods here, a few functions that implement some code. And then we can, the researcher can tell, okay, I'm interested in Hytila. There's a function here to read the semantic descriptions of events into data frames. So we have a function here that does this, fetches from the catalog directly all the descriptions for new particle formation events and converts the semantic descriptions in REF into a data frame format. And you can see this is ideal then for further analysis of this event information. You can see here a print of the data frame. So we have here in one column the beginning, the end of the event, the classification, the place where it occurred, and also latitude and longitude. This is basically also all extracted from the semantic descriptions cataloged in the CCAN instance. And then we can simply process this data frame as we do in data analysis. You can use the full power of Python here to, for instance, compute a mean duration of events. This is done in this code here. We can print the duration, the computed duration. This will be 2.6 hours. And we can record this duration and back into as a semantic description. So not just the value 2.6, but a description that this is in fact the duration of 2.6 hours. And we have a meaningful semantic description of this object here, of this data point. We record this into the catalog, and you can see here an example. Back to the catalog, and you can see here there is another item here for computed mean durations, and I did this ahead. So we have here a computed mean duration, and we can look at it as before. so you have a number of things here, but in particular, a description of the mean duration. This is an entity, prof entity computed in data analysis. And this is a little bit cryptic, but this is OBO foundry ontology term here that you can also look up on an ontology service, that basically is the value of the mean duration, and there is the unit of hours here. This is also a term of an OBO foundry ontology that I'm using here. So this is also an example. So you can see here the unit here has a label hour, and this is also an example for how we can acquire a semantic description of these 2.6 hours rather than just having the value alone. Good. And finally, I like to show you also, since I've been talking about provenance, I can show you also how you can process provenance. So in executing this analysis, the system acquires quite a lot of provenance for which entities were derived from which other entities, which agents were involved in this computation, and which activities were executed. And this provenance is automatically generated by the infrastructure and also stored. And you can, of course, process this provenance. And for this, we have an example notebook also here. Again, G-cube code or token, and then a number of a couple of functions here that implement some functionality to read the provenance information from the catalog. This provenance information is also cataloged in the CCAN instance. And then we can execute here Sparkle queries. Since it's all in REF, we can execute Sparkle queries to read this provenance information, in particular which entities, entity 2, are derived from entity 1. So this is, for instance, we have here a plot that is derived, so is used to derive the description of a new particle formation event. So a new particle formation event description is derived from an interpreting of data visualization of the plot. And this entity is generated in an activity, and I'm looking here at the label of activity, and I'm also extracting at what time this activity was executed. And since I did a couple of data visualization steps, as well as an arithmetic mean calculation activity, you can see here the provenance information here, that we have here an entity 2 that is derived, and we have the identifier of that entity, but you could look at this entity up. This is a description of a new particle formation event. That was computed from an entity 1 or via an activity of data visualization. So not just computed, but a human being has interpreted this plot here, entity 1, and generated the description of the new particle formation event through a data visualization activity. And we also have the time, and we did this for 3 days at Hytjala. Therefore, we have the 3 activities here of data visualization, and then we computed the mean duration of these events that we have cataloged. And this would be the 4th entry here as an activity of arithmetic mean calculation that was executed at this time. And you can see here that this would be the identifier of the information object that describes the computed duration, so the 2.6 hours. And this is a reference to the data set that was used in computing this. So the set of events that we used here to compute the duration. And I can show you finally in the catalog also how the actual plots are also stored. So not just the description of the new particle formation events, but we have also here references to the plots that are also cataloged as research objects here in the catalog. Okay, thanks for listening.